All right, hey guys, welcome back. Um, so, if I get, this will be a shorter lecture today. I'm not going to talk a whole lot. So you guys will have the rest of time when I'm done to just work on activities and ask questions if you like. I just want to do a couple examples of some simple probability problems, sort of in the style of a couple different problems that you might see on 8.1b, that activity. I just want to point these out. I think last time I taught this class, I didn't talk about these specific types of problems explicitly, and some students ended up being confused. And so I figured I would just do a couple examples on the board for you guys to make sure that I have shown you this type of problem. So if you've not looked at 8.1b yet, you will see what I mean when you do. So let me go ahead and get on with these. I'm just going to do a couple example problems, basically, is all I'm going to do today. So this will be helpful for you on your activities. So I just want to remind you, this is just a basic property of probability in general. If I have a sample space, so I guess I'll say this first. Just remember that the sample space for an experiment is the set of all possible outcomes. So I'm just collecting all the possible outcomes of some experiment or something, right? So if I flip a coin, the only possible outcomes are heads or tails. If I roll a die, the only possibilities are the 6 numbers on the dice, right? And so forth. So just collecting all the possible outcomes. So if my sample space is, I don't know, and it has outcomes x1, blah, 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 up through x, just some number of outcomes. Say these are the possible outcomes. I'll just call them x something. Then when I add up all of the probabilities of each individual outcome, what happens? Well, I'm going to get 1. So if I have all the possible outcomes for some experiment and I add up the probabilities of each one, I'm going to get 1. This is kind of a dumb thing, not a dumb thing to say, but this should sort of be quote unquote obvious just from the fact that I know that for a single outcome, the probability of that outcome happening is just 1 over however many things are in the sample space, in this case n. It's just 1 over n. And if I have n outcomes, that means I have n 1 over n's that I'm adding up. Well, that's just n times 1 over n, I'm going to get 1. So it's not that interesting when I just look at individual outcomes like this. What's a little more interesting is if I look at events. But, well, okay, let's just leave it at this, I guess. So this is really what I want to say is if I add up all the possible outcomes, I get 1, right? I will get 1. Because basically I'm adding up all the possible probabilities. If I take all the outcomes, I'm covering all possibilities. Therefore, it has to be 1 because, I mean, one of these outcomes has to happen. So I should get 1. OK. So I want to apply this idea to solve some problems. And this is useful for us because recall, this is something that's going to come up a lot. So recall again from yesterday. What did I tell you guys? The rows of a transition matrix add up to 1. They each add up to 1. So I wrote some transition matrices on the board yesterday. I can't remember exactly what they were. I think one of them was something like this. Maybe the numbers were in different spots, but it was something like this for that weather example from yesterday. This is our transition matrix. And we noticed that the numbers in each row add up to 1. So 3/4 and 1/4 add up to 1. 2/3, 1/3 adds up to 1. And I could sort of relate it to what I just told you because if this was the sunny row, and this is the rainy row, and this is sunny column and rainy column, if I already know that today is sunny, and I want to ask what's the probability that tomorrow is sunny or tomorrow is rainy, well, those are the only 2 possibilities. And so this row basically represents the only possible outcomes for the next day, where I've already assumed that today is sunny. So these are the only 2 possible outcomes now after today is sunny, is it's either going to be sunny again or it'll be rainy. And since those are the only possible outcomes, aka those are sort of like the only elements in my sample space in this situation, the probabilities of each of them have to add up to 1 because they're the only possibilities once I've assumed that it's sunny. Same thing for rainy. If I assume today is rainy, the only possibilities are it's either sunny tomorrow or it's rainy tomorrow, right? Those are the only possibilities. So the probabilities, again, need to add up to 1 because nothing else can happen. So I've exhausted the possible outcomes, so the probabilities have to add up to 1. Okay, so this is going to be important when we talk about transition matrices. There are some problems in 8.1b that are sort of exploiting this property of adding up the probabilities of your outcomes and getting 1. And we can sort of use that to solve for probabilities. And so I want to show you a couple examples of that explicitly, using this property to solve problems. So I'm just going to do a couple of these. Here's how it goes. So you'll find problems stated similarly to this on your activity. So let's do this sunny rain example again, just because it's gives us a nice example to use, although the probabilities will be different now. So suppose the following, that it is 3 times as likely to be sunny today, or maybe tomorrow, let's say tomorrow. It's 3 times as likely to be sunny tomorrow as it is to be rainy. I don't know if that's the grammatically correct way to write this, but good enough. So we'll suppose that tomorrow it's 3 times as likely to be sunny as it is to be rainy. So what is the probability of each one? Of rain / sun. So I want to find, there's 2 probabilities to find, the probability that it'll be rainy tomorrow and the probability that it'll be sunny tomorrow. I claim that I've given us enough information to solve this already, just by saying it's 3 times as likely to be sunny as it is rainy. So how is that? You know, if you notice the problems that I gave you before when I introduced Markov chains, I basically gave you each individual probability explicitly. Here, I've just told you one thing. 3 times as likely to be sunny as it is rainy. So I have to do a little bit of work. I'm going to have to set up an equation and solve it to find each probability, because I don't really have anything to go off of other than this fact here. So what do we do? Well, we got to remember what I just said. There are only 2 possible outcomes in this scenario. It's either going to be rainy or sunny tomorrow. We're not allowing for any other weather phenomena. So it'll either be rainy or sunny tomorrow. Those are my only possible outcomes. So when I take the probability of each one, they have to add up to 1. That gives me an equation that now I can exploit. I'm going to have some equation that sets the sum of my 2 probabilities equal to 1. So just to make it really precise, let's introduce some variables for these probabilities, because I don't know what the probabilities are, but I would like to know what they are. So why don't we just set x equal to the probability of rain tomorrow, and y will be the probability that it's sunny tomorrow. Okay. Just make some variables like this. This will give us something to play with that maybe we can then put into an equation and solve. Okay. So on the one hand, what I just said is that the probabilities have to add up to 1. So I know I have one equation which says this, that if I take these 2 and add them together, I better get 1. Because these are the only possible outcomes in my sample space at the moment. So their probabilities have to add up to 1. Okay. So I have this equation. We're a little in trouble though, because I can't solve one equation with 2 variables like this. You know, there's infinitely many solutions to this. Something else then that I need is this other bit of information which I haven't used. It's 3 times as likely to be sunny as it is to be rainy. So I want to translate that statement into math with these variables so that then I have another equation. Well, if it's 3 times as likely to be sunny as it is to be rainy, what does that mean? It means that the probability of sun is 3 times as much as the probability of rain, i.e. y is equal to 3x. It's 3x. This is saying that y is 3 times as much as x. Okay. So I now have another equation. I have these 2 equations. This is good. Because now, what do I have? As it always happens in this class, it seems, it all reduces down to being a system of equations that we have to solve. X plus y equals 1, y equals 3x. I need to solve this system of equations. When I do, it should tell me what the probabilities of each one are, because that's what these variables represent. So we would just solve this system and we'd be done. So, you know, y being equal to 3x, I could substitute this into this equation up here so that then x plus y is really x plus 3x equals 1. Collect like terms over here, that's 4x equals 1. So it looks like x is a fourth. So already x is a fourth. And it's good to check as we go, you know, this is supposed to be a probability of something happening. And I told you guys the other day that probabilities have to be between 0 and 1. Well, 1/4 is between 0 and 1. You know, in decimal form, this is 0.25. So that's between 0 and 1. So this really is a number that makes sense. It's good to ask yourself that as you go, you know, are the numbers I'm getting make sense? This makes sense as a probability because it's between 0 and 1. Now that I know x is 1/4, well, I'm just going to plug it back in up here. What do I need to add to 1/4 to get 1? Well, it turns out y is going to be 3/4. So there's a 1/4 probability of rain. There's a 3/4 probability of sun tomorrow, according to this scenario. So that was all the information we needed to be able to solve this. Just that the probabilities add up to 1, and that we were told that it was 3 times as likely to be sunny and rainy. So this fact is going to come up again and again as we work with Markov chains. So it's just good to get used to this now. The probabilities have to add up to 1. Okay. I'd like to do one more of these. That's just a little more, just going to up the complexity a little bit. But show that basically the same approach will still work from there. So let me do one more of these. So here's another example. Let's introduce another weather phenomena into our